Thanks for coming to the next installment of the Quantum AI speaker series. And I would say this talk is a little bit of an experiment in the sense that, of course, at Google, most engineers have a background in computer science. And this is a widely announced talk, so you might ask the question, why the bleep should somebody in computer science listen to a notable condensed matter physicist? And I wanted to use this introduction to answer that. Actually, earlier this week, there was a White House meeting on quantum information science, and essentially to chart the US government's strategy for funding of this area, which they consider to be of strategic importance. And there was a colleague of ours, Seth Lloyd, who made an interesting observation. He was saying even prior to the arrival of larger quantum computers, quantum information science has already been tremendously successful in the sense that it has provided a common language that are now used by different areas in physics and computer science. And if you think about it, it's kind of true. For example, when we designed the random circuits for a quantum supremacy experiment we tried to attempt, then I remember that Sergio went to see a black hole physicist at Caltech to discuss those circuits. Because as far away as these areas sound, what has a black hole to do with a quantum computer, turns out they use methods very related and useful to Sergio's analysis. And in a similar way, condensed matter physics turns out if you ask the question, how does an electron get from one place to another in a conducting metal, this question is not too different in the methods you will apply from asking the questions, how does a quantum annealer, a quantum enhanced optimizer, get probability moved through an optimization landscape. So in that sense, I expect quite an explosion in insights that very sophisticated pockets of expertise are suddenly being interlinked, and we start to think in very new ways about old problems that with classical methods alone seem to have saturated, but now suddenly it opens up. You think about it differently because quantum information science methods can be applied. And in that sense, I'm very happy that Boris Altshuler, who is one of the grandmasters of condensed matter theory and well known in sub-areas such as many-body localization, many-body delocalization, volunteered to give sort of a bit of a tutorial talk that hopefully to some degree is amenable to computer scientists as well. So Boris has a very distinguished career, and I will brutally shorten his resume. So currently he's at Columbia University, New York, professor there, but previously he held faculty positions at Princeton and at MIT. He has a long list of prizes to his name. He's a member of the National Academy of Sciences and the American Academy for Arts and Sciences. And he actually comes from the School of Russian Analytical Physics. And yeah, we are very glad to have you here and hear your talk.
I have mine. Can you hear me? So first of all, thank you very much for inviting me here. I really enjoy, and every time I'm coming here, I learned a lot. And second, that's right. There is no really disconnected parts of physics. Physics, and especially quantum physics, is unique. And it turns out that quantum computer is yet another quantum system which has a lot of advantages from the point of view of pure science. So let me first very quickly tell what is, to my mind, the main feature of the quantum computer. So in classical case, we have these bits, and what we are doing certain manipulations with these bits, which are dictated by the code that we are using. And in the end, we get an answer in a form of a bit string. Now, if you are dealing with quantum computer, then at the end of the day, you want to get a normal answer, which also is coded as a bit string. But in the middle of the computation procedure, in the middle of this manipulation, the state of the quantum computer is not a particular bit string, but kind of quantum superposition of these bit strings. So in a sense, if you want to use these bit strings as a basis, which, as I learned, is called computational basis, then in this Hilbert space, we have a wave function that characterizes this quantum computer. And our manipulation will, what we are doing, we are trying to design and tailor this wave function in a way that it will contain desirable answer as a major component of this wave function. So the most, of course, important is what kind of manipulation, what is the quantum algorithm to get this answer. But I'm not in state of discussing that. There are in this room many people who know about the quantum algorithms more than I do. So I will probably play a role of this small boy who is sitting on the shoulders of serious people, and all of them are looking on this dog, and people are solving serious problem how to get this dog eaten. But this small boy just thinks about all these stupid hydrodynamic equations and what makes the bird fly and so on. So let me play this role. I will just will try to put this quantum computer into the context of generic quantum system with large number of degrees of freedom, and try to kind of introduce you to the language in which we can discuss it. And actually, it turns out that almost any quantum computation can be reduced, maybe in a rather sophisticated way, to some particular universal Hamiltonian, where the degrees of freedom are these quantum spins and qubits. And this Hamiltonian consists of two parts. The first part is involving only z components of the spin. So if it would be a classical bit, this is all what we have. And in principle, it is written in a form of just generalized Ising model. So we have these spins. Each of them is subject to some magnetic field in the direction B. And there are certain coupling between them. And we don't have any particular geometry in mind. So Jij can be represented by certain graph, or so any spin in principle can be connected with any other spin with this exchange. And the second term is transverse field. So this is field that in principle can rotate our qubit. Now, what is important, I hope you will appreciate that, is that in the absence of transverse field, what we have here, we have a Hamiltonian such that every Ising spin, every bit is operator of Ising spin commutes with the Hamiltonian, which means that looking on this system as a quantum dynamical system, we have actually n conservation laws, because each qubit, when when it is governed by the Hamiltonian without the transverse field is conserved. And this conservation law is violated by the transverse field. And you will see that this structure of the Hamiltonian, that one part that has a huge macroscopical number of conserved quantities of integrals of motion, and another violates it. This type of the Hamiltonian is quite generic and has a lot of problems that are common for the whole class of different systems, including quantum computing. So to give you another example is completely from condensed matter. If you have a conductor and there are electrons which are subject to a random potential, static time-independent random potential, and at the same time interact with each other, you can also argue that when you forget about the interaction, each particular particle is in its own state. Each states are characterized by the occupation numbers, and these occupation numbers will not be changed as long as there is no interaction between particles. But as soon as there is interaction, they will collide and change the occupation numbers. So I want to go even further and try to make a comparison between what happens in the quantum world and what happens in the classical world. So if imagine that you have certain, as people call it, dynamical system, classical or quantum, which has a large number of degrees of freedom. And then very roughly you can separate this world of these dynamical systems into two classes. One is integrable. And if we are thinking in classical terms, it means that you can separate the variables. So you think you have one problem of d degrees of freedom. At the end of the day, you have d problems of 1 degree of freedom. And in classical mechanics, this is, in a sense, trivial. And if you indeed can separate variables, then you have as many conservation laws, as many integrals of motion as you have degrees of freedom. And on the other side of this class of models, there are those which we have in mind when thinking about thermodynamic and statistical physics. Then we assume that this astronomically large number of degrees of freedom leads to what they called equipartition distribution of the probabilities. So in a sense, we assume, it's a basic principle of statistical mechanics, that probability to find an isolated system in two states with equal energies are equal, regardless to what is their history. And it is interesting to follow what happens when you go from the purely integrable system to purely chaotic, which can be used as a subject of statistical physics. Or there is another word which I will pronounce several times, which is ergodic. And as I told, in the middle, there is quite interesting evolution. So first of all, if this lambda, if this violation of integrability, violation of symmetry is very weak, there is very well appreciated in mathematics Kolmogorov-Arnold-Moser theorem that tells you that provided lambda is small enough and perturbation is smooth enough, you don't destroy integrability immediately. But it turns out that even outside this region, when all estimations following this CAM theorem proof show that there should be no integrability, still we have a system that does not, systems that do not demonstrate anything like complete health. So the first system I want to mention is so-called Fermi-Pasta-Ulam system, which is kind of model that probably was the first model that was numerically treated because these three gentlemen were working in Los Alamos and just got a first supercomputer at that time. And what they tried, following Fermi's idea that if system is not integrable, it should pretty quickly get into the chaotic state and all modes will be mixed. They considered the chain of connected nonlinear oscillators and found that they simply could not get into the situation where all modes are mixed. In a sense, it turned out that system actually remembers its original state. And another system is even more familiar for us. It's solar system. So I hope there is no need to discuss what I'm speaking about. There are these planets in the, flying in the field of the sun, and Isaac Newton calculated the orbits, but in fact, he calculated them assuming that each of them interacts with the sun, and neglected the interaction between these planets. And it's not that he was not bothered about this approximation. He was actually bothered a lot because for him, the periodicity of the world and the perfectness of all the dynamics was kind of not negotiable. And at the same time, he was smart enough to understand that interaction between the planets will violate this perfectness, and the dynamics will not be periodic as he wanted. And he was worried to the extent that he even assumed, imagine Isaac Newton assuming that there is God which once in a while intervenes and puts everything back into this perfect trajectory. And then there was discussion, for instance, with Leibniz, who there was mutual unpleasant relations between them, and Leibniz told that this is a bad idea to reduce God to a simple miracle. Anyway, what do we know about this solar system? We know that indeed having computers, the best computers of today's time, and smart people who are doing that, you can make these algorithms and predict the state of each planet pretty well in the future, but only up to about 100 million years, maybe a little bit less. And after that, it becomes unpredictable. And the reason is that motion is indeed, motion of the planets is indeed not integrable. And this chaotic component takes a toll, and a system kind of starts depend on this original conditions pretty strongly, so that each, for instance, if we will go and close the door in this room, in a couple of billion years, the orbit of Jupiter will change its phase by something of order pi. So this system is not integrable. You cannot come up with exact conservation laws, but at the same time, it is not at all completely chaotic, and the only big, as far as I know, the only big catastrophe could be that with probability 1% before Sun explodes, there would be collision between Mercury and Venus. But nothing more than that will really cause this chaotic motion. And the final classical system that I want to mention is kind of whole class of systems which are glasses. And again, we know that although glassy state is not equilibrium state, and in the equilibrium this system should become a crystal, but they found glass on the moon, which means that a billion of years is not enough to actually crystallize a piece of glass. So it means that there are systems which are intermediate between very well predictable, integrable, which conserves all these integrals of motion, and chaotic, which does not. So the way to think about it that I propose is the following, that let's start with integrable system. We are speaking about only H0, only about Ising part of the quantum computer Hamiltonian, or about interaction between planets and sun. Then there are these integrals of motion, and full set integrals of motion determine so-called invariant tori, and every trajectory depending on original condition is on this particular tori, provided it has this set of the integrals of motion. So if you are monitoring the behavior of your system in the space of quantum numbers, then the point that is in the space of integrals of motion, there will be a point which is not moving with time. And the difference between quantum and classical is not so big. The only thing is that this space of quantum numbers is quantized. It's not continuous space anymore, but it is quantized, and each side of this lattice corresponds to some particular state of the integrable quantum system, which is characterized by a set of quantum numbers, like in atomic physics. And if we are dealing with this quantum computer, it is probably the set of bit strings, and this lattice looks like a d-dimensional hypercube. And for instance, if we are monitoring the motion of a particle inside a rectangular billiard where both horizontal and vertical momenta are conserved, we have just square lattice that corresponds to these allowed values of the momentum. And now the question is, what is happening if you apply this perturbation, which does not violate this integrability, which does violate this integrability. And then, of course, this point, which was not moving at all in purely integrable system, will start to move. But if you are in a calm region, then it will not go too far. So the calm statement in this representation is just the fact that this trajectory will be kind of demonstrating the finite motion. And what happens? What does it mean for quantum system? for quantum system, it suggests that on this line, which is energy shell, which is a line that corresponds to given energy of your system, there will be only a small part of this energy shell in which our system will live. So there will be only a small number of the original states of this integrable system that are involved in the eigenstate of the perturbed problem. So the difference between the chaotic and integrable behavior is that chaotic behavior would mean that this wave function is present all over the energy shell, and integrable means that it is only one point, and we have this intermediate situation when it is neither, and wave function occupies a small part of this energy shell. And this phenomena is kind of analog of the Anderson localization, only instead of localization of wave function of a particular particle in real space, like three-dimensional, two-dimensional, or one-dimensional space, we have localization of our whole quantum system in this space of the integrals of motion of the original integrable problem. And just to remind you quickly, this all started with the discussion of the diffusion. So you can ask yourself, if you create certain narrow wave packet or a classical particle that is located in a certain point, and then it's subject to some kind of random walk, then it was a famous paper of Einstein in the beginning of previous century that told that the probability to find this particle at certain distance is governed by a diffusion equation, and in particular, mean square distance is increasing as a time. And what Anderson told that for quantum systems, it might be not the case. And instead of increasing the mean squared distance from the original point, can saturate and remain finite even when time goes to infinity. And this means that if we are in a certain quantum state, this state will evolve, but if all components are localized in the same part of the space, you will not go too far. And this is just cartoon how these eigenfunctions of a particle in a random potential, how it can behave. It might oscillate very rapidly in real space, but it can be that the wave function has this envelope which decays exponentially from certain particular distance, and this means localization. And to justify this conclusion, Anderson used the model which is of interest for us. It's now called Anderson model, and it's basically tight binding model. So you have a lattice. Each side of the lattice has can host a quantum particle. You have one particle for the whole lattice, and you can tunnel or hop between nearest neighbors on this lattice. And the only difference of this from conventional tight binding model is that on-site energies are not equal to each other. Instead, they are randomly distributed in a certain interval, and width of this interval, which is W, is characteristic of your system. And if you fix this tunneling amplitude as 1 between the nearest neighbors, then this W becomes a parameter theoretical study. And claim of Anderson was that there is critical value of W, and if W, which is bigger than its critical value, if disorder is strong enough, all states are localized. If disorder is weak, the states can be extended. And then it was understood after a lot of numerical and theoretical work that a particular model is not as important, and you can consider all kinds of modifications of this model, but this qualitative conclusion is robust enough. Now, just some intuition about how you can think about this localization. So to start with, let's consider something ridiculously simple. So let's consider Anderson model of two sides, which is also known as two-well potential. And in this case, when we have two states, each belonging to one well, and some kind of tunneling amplitude, you can consider this system as Hamiltonian of this system as 2 by 2 matrix, and there are, depending on the parameters of this matrix, there are two possibilities. Either these states are off resonance, so difference between diagonal matrix elements is much larger than off diagonal one, and then basically this possibility for tunnel will cause only small perturbation of the original wave functions. And opposite situation is resonance, when the diagonal matrix elements are almost the same. So without tunneling, the two levels are almost degenerate. And then your resulting wave functions will be neither wave function in one well or in another well, but it will be rather the bonding or anti-bonding combination of these two states. So in a sense, in this situation, a particle will belong equally to each of the two wells. And now, when we are going to a bigger system where there is more sites with random on-site energies, when we have this randomness very strong, there would be only few resonances, and they will be very much separated from each other, and then the states will be localized on one or maybe two neighboring sites. But when you keep reducing disorder, you will get more and more resonances, and they will start to overlap, so you will have not 2-level but 3-level resonances, and so on. And at the end of the day, you will get extended states. And you have this, can estimate the transition point. Now, just 2 words about experiment. I always like to show this picture. So you make microwave cavity, and then you mimic disorder by something that you are not supposed to do. You put some metallic particles inside this cavity. And what people did, they analyzed distribution of the intensity of the electromagnetic field and found that depending on the frequency, this distribution is either strongly localized in some particular small part of the system, or is extended. So it's not uniform, but it is present everywhere in the system. And another example, which people in France, and also there is analogous experiment in Italy, did. It is from the field of cold atoms, when you create first a point like trap and put your atoms there, and then you allow them moving in one direction, but you mimic the random potential by some complicated laser speckles. And what you observe is that this wave packet doesn't want to spread. So coming back to many body systems or systems with many degrees of freedom, what you can tell is that you have this lattice, whatever it is, and you have energy shell. And if matrix elements of this perturbation that violates integrability are connecting only relatively close points in this lattice, you have the same arguments, and you have something analogous to the Anderson localization. So basically, you can justify Anderson model for almost any Hamiltonian which consists of these two parts. And coming back to this quantum computer Hamiltonian, it is almost exactly Anderson model on d-dimensional, or here it is n-dimensional hypercube, because the operator sigma x is just sigma plus plus sigma minus, and it means that what this second term in the Hamiltonian does, it flips a spin either from up to down or from down to up, and this is exactly the same as transition between the nearest neighbors. And so basically you have this something like Anderson model only on the large dimensional hypercube, and in principle it looks like situation is different because this cube has a linear dimension 1, but actually what is important is that distance between different points on this hypercube can be as big as the number of the spins, so-called Hamming distance, and number of sides is huge. I just now you can steal almost anything on the internet, and this is 6-dimensional hypercube. This is projection of a 9-dimensional hypercube, and probably a much bigger hypercube is a huge system, even though linear size is equal to 1. Okay, now what can we tell as from the point of view of statistical physics about these many-body localized states? The states which localized by definition means that if I start here, I will stay here forever. If I start here, I will stay here forever, which means that there is nothing like equipartition, and all arguments of statistical physics are not applicable. You cannot introduce temperature. The only thing you know is that you have quantum states, and these states have certain energy. So, for instance, entropy is not increasing with time if states are localized. So, for localized states, our usual approaches are not applicable, and the question is what happens if we undergo the Anderson transition? Is normal picture appearing immediately after the transition or not? And in fact, to have some kind of clue of what is going on, it's again interesting to think about the classical system. And I have to admit that there is kind of big difference of approaches of mathematicians and physicists. There was a joke that if a physicist wants to, is asked to calculate the stability of a table with 4 legs. He first does problem of table with 1 leg, then infinite number of legs, and then the rest of his life works on table with arbitrary number of legs. And what is lacking in most of mathematical papers is the second step. So most of the problems of the transition between integrable motion and chaotic motion are done for systems with 2 degrees of freedom, and nobody yet was really building mathematical theory of a system with high number of dimensions. But there was still important step made by Arnold, and his statement was interesting. I will try to explain you how it goes. So if you have 2 degrees of freedom and you violated integrability, but the tori's still exists, only are deformed, then even if there are only few tori's in the system, still if you are starting inside some tori, you will always be there. If you are outside, you will always be there. Because the dimension of the space is 2 dimensions. Dimension of the phase space is double because coordinate and momentum. It's 4-dimensional. Energy shell is 3-dimensional. And tori, remember, it is just where the particular set of the integrals of motion is realized. Tori has dimension equal to dimension of the space. So we have 2-dimensional tori in 3-dimensional space, and it's clear that we are always either inside or outside because trajectory cannot cross any tori. Now, when you are going to higher number of dimensions, let's say 3, then difference in dimensions between the tori and energy shell is bigger than 1. So in sense, what we have not like a tori in 3-dimensional space, but a circle in 3-dimensional space. And circle does not have inside and outside. And what happens as a result is that even when this perturbation is infinitely is very, very weak, but finite, then there will be still certain trajectories that go and cross these existing circles many times. And as a result, you can get in the energy shell arbitrary far. And this process is known as Arnold diffusion. So that at least some part of the probability will be actually diffusing. And I think this phenomena, which is rather weak in 3 dimensions, becomes dominating in very high number of dimensions. So this is just 2 systems which I wanted to discuss, but I don't want to. I don't have time to give you more details. It is either transport of interacting particles, where you have certain interval of temperatures in which there is no conductivity at all, or you can also study the Josephson array, and you can find that there is also behavior which corresponds to localization in this Hilbert space, and there is part of the phase diagram where we have ergodic behavior, but in between there is a new state, a new type of behavior which we call bad metal that corresponds to this non-ergodic but extended state. So this is more or less the evolution of generic evolution of our system when we change, when we increase the violation of the integrability and go from the insulator to ergodic metal. And as we believe now, there is not one transition that was predicted by Anderson, but two transitions, one from insulator to non-ergodic metal and another from non-ergodic to ergodic one. Now, how much time do I have? Okay, I think it would be enough. So, a few words about ergodicity. The way of thinking about it is the following, that if you have just some generic problem like Anderson model, then there is, as I told, critical value of the disorder at which Anderson transition happens, and there is also at any finite system there is usual critical behavior where a system is neither localized nor extended, because this critical volume of the system diverges when we approach the critical point in disorder. And the way to analyze these wave functions is the following, that you can consider so-called moments of inverse participation ratio, which are these sums of wave function to the power 2q, where q is in our hands. And of course, this wave function is supposed to be normalized. So for q equal 1, we always have 1. But as soon as q is not equal 1, then these quantities should somehow scale with the system size. So they should be proportional to the total volume, total number of sites in the lattice to some negative power. And just to make simple estimations, if everything is ergodic, is every site is more or less occupied, then since wave function is normalized, its square on each side is inverse proportional to the number of sites. When you take it to the power q, it would be number of sites to the power minus q, and sum in the definition of this moment of inverse participation ratio will give you 1. So all in all, this exponent will be equal to q minus 1. Now, if we have, if we have a localized state, it is clear that if wave function is present only on finite number of sites, then all these moments of participation ratio are independent on system size, and all tau q's are equal to 0. And the reason why I'm speaking about ergodicity is that you can show that if tau q is exactly equal to q minus 1, then averaging over space is equivalent to averaging over ensemble of different realizations of disorder, and it kind of resembles the definition of ergodicity that was given by Boltzmann, who called by ergodicity the fact that average over space and average over time is equivalent. Okay, If everything is ergodic, then these exponents are equal to q minus 1. If everything is localized, then they are equal to 0. And in a generic case, when it is neither 0 nor q minus 1, you can introduce ratio of these particular exponents in q minus 1. And this ratio is called fractal dimension. So there are, for each q, there is certain fractal dimension. And this situation when all the q's are different is called multifractality. Now, if we are dealing with ordinary three-dimensional Anderson transition, then there are serious possibilities to believe that this multifractality takes place only at the critical point. So as soon as you are out of the critical region, situation becomes either ergodic or localized. But it is probably not the case in the for many body localization. And the reason is that if you are thinking about the Hilbert space and think about how many states are connected with this particular state in nth order of perturbation theory, this number increases exponentially with n rather than in a polynomial way as it does in a finite dimensional space. And because of that, it is much more probable to have resonance on the large distance. And as a result, the wave function of after delocalization still can be imagined as a certain number of more or less separated large peaks. And of course, in this situation, when we have wave function which is consists of some number of peaks that are far from each other, there is no ergodicity because there are so strong fluctuations. Mm-hmm. So I will probably skip this story about Anderson model on the beta lattice, which allows kind of make poor man's calculation and demonstrate that there is indeed a big region in the parameters where the wave function is neither ergodic nor localized, but rather multifractal. And now the question which we yet have to understand is how to use this type of wave functions. And from generic point of view, it looks very tempting to make this quantum computation in the region where the wave functions of our system are indeed multifractal and consists of several separated peaks, because this type of wave function actually contains a lot more information than is a localized or fully ergodic state. So let me finish here. My time is over, and thank you very much for your attention.
So we are just at 2 o'clock, but maybe 1 or 2 questions for. No questions? Then I think we.
I have a question.
Yeah.
So what is
Vadim, you see a microphone, please.
Yes. Given this phenomena that you describe, how do you think potentially this could be of application to field of machine learning? In a very broad sense, without.
Well, in a broad sense, I think it is the following, that if I understand correctly, what you start with machine learning is giving a certain number of examples. For instance, you show a picture which is a set of pixels and call this is a dog, this is a dog, this is a dog. And all pictures are different. And then what you want to create, you want to create kind of idea, abstract idea of a dog. And if you just have, large number of particular pictures, what you can do, you can form a state which is linear combination of those. And then this looking on in some sense on the scalar products of this state with the picture which you should recognize, you can probably get some idea. I think this is the way how our brains should think when they make these ladders of generalization. They take particular examples and form kind of linear combinations of them.
Okay, thanks.
So maybe adding to Vadim's question, since you asked already about machine learning, and this is your last question, if you may, or if you would be so kind to speculate, how do you think we could use such non-ergodic states in quantum annealing?
No, but you see, suppose we're discussing exactly the problem which we discussed yesterday, that you found some state with low energy, some solution, some bit string which corresponds to low energy, and we want to find another one which also corresponds to low energy. So imagine now that there is a wave function which is formed by states localized here, near one solution, near another solution, near a third solution. And these states are close in energy. Now, when we decrease disorder or increase the transverse field, what we are doing, we are hybridizing them. So true states of our system in this region of energies will be a kind of linear combination of the solutions. And then if you put your system in one of the states, then it will be a linear combination of these states with nearby energies in this particular point. So all states with, with these peaks, symmetric, antisymmetric, all states which were obtained by n nearby states will have the same form. And if originally they are adding with only one peak, after you allow them to evolve and have generate some phases, you will unavoidably grow another peak and then yet another peak and so on. So in this sense, if you are having this multifractal state, what you will have continuously increasing probability to get into new solution or new approximate solution. So in a sense, if we have this type of structure of wave functions, it is very, it's much better than going through ergodic state, which contains no information about the structure, just distributed completely. And of course, if we are already in localized regime, it's also bad because then you will never go.
I have one more question. If you think of a quantum computation as a quantum state evolving with a time-dependent Hamiltonian, and you look at the state, which is a time-dependent step that you're preparing in the computation, do you think this will be multifractal or localized, delocalized?
It depends on transverse field. So as I told, if your transverse field is large, not infinitely large, then it dominates. But large enough, you might, in principle, have, I think I should show you this phase diagram. So if your transverse field is very large, and here it's vice versa, the transverse field is equal to 1, but the Z field is increasing, this W. So if W is very, very small, you are in this red region, which is ergodic. And only in the edges of the band, you start to have this non-ergodic state. But when you increase the disorder or decrease the transverse field, you will get into green region when you have more non-ergodic state. And the further you go up, you will have this states, these fractal dimensions smaller and smaller. And if you go too far, you will get into localized regime. So depending on this transverse field and on your energy, you can deal with different states. And I think this is generic for more or less any Hamiltonian.
So I think you're talking more about quantum annealing, and I was thinking it wasn't very clear on a gate model quantum computation, where a gate model quantum computation, which I think if you express it in that Hamiltonian will also have a time-dependent transverse field. And
but what I learned, maybe now it is disproved, but there is some kind of mathematical paper with large number of authors that any even circle quantum algorithm can be reduced to the quantum annealing of this type. So I think this way of thinking is even more generic than it looks like.
Okay, maybe we should conclude here. So thanks, Boris, for the very informative talk.